All right, finally we get to inverse tangent functions. So this formula over here is given to you on your standard integral table, all right? But it's good to be familiar with it. So here we have that the integration of 1 on a squared plus x squared equals to 1 on a inverse tangent x on a. So this 1 on a here is what most students get confused and forget. All right, so if we know the integration of this gives me inverse tangent, then I can work out that the differentiation of inverse tangent must give me that. But be careful because there's a 1 on a in front. Now, working out the derivative and making sure there's a 1 on a in front is going to be really difficult. So the best way is to change this formula a little bit. So what I'm going to do is multiply this a over here, okay? So if I multiply that a over there, then this just becomes 1 times inverse tangent, which essentially is just inverse tangent, isn't it? So I know that the derivative of inverse tangent x on a equals to that a multiplied over there equals to a on a squared plus x squared, okay? And this here is what we'll be using throughout. So I think it's really good because even though this is what's given to you, it's really important you're able to, from here, go to this step to work out differentiation, and then from this step, go to this, yeah? So this is given to you, we have to go through these steps, and it's probably just on your standard integral table. It's good to just generally quickly write that, okay? And then you can refer back to it. All right, so this is what we'll be working with. Let's have a look at the general formula now. So all we've done here is a equals to 1. So 1 on 1 just disappears in this case. And here we have this 1 is just from a squared substituted in. So that's why it's just 1 on 1 plus x squared. So these two equations, this general formula here and this are the two things that we'll be using throughout the questions. All right, so there's a little bit more work with tan because you do need to go through those steps to get there. But remember, this is given to you. So it's not really memorizing that's a problem. It's just kind of using it and finding the easiest way to apply your integral formula to differentiation. All right, so I always want to start off with proving why the derivative of this does equal to that. So I'm going to let y equal to inverse tan x, switch the input and the output and make the inverse tan into tan, and differentiate the tangent y, and that becomes sec squared y, and that's dx on dy. But remember, what I want to find out is dy on dx, which means I need to flip it. So that becomes 1 minus sec squared y. And now I need to use a trigonometric property, as I did before, and this property is going to be, remember that sec squared equals to 1 plus tan squared, yeah? So that is your second property in your trigonometric properties. All right, so knowing that, that means I can just change sec squared into 1 plus tan squared. Now, knowing that x equals to tan y, I'm going to change that into x squared. And that's how you get that dy on dx equals to 1 on 1 plus x squared. And it makes sense here why this is 1 plus x squared, because it's similar to 1 plus tan squared, yeah? So can you see how there's always a reason for these things? And I think it's really good to know the proof for them before you move on to actually answering questions. Because once you get the basic concept of something, it doesn't matter how difficult the question is, you're just applying those ideas and then working with it. All right, let's work through some questions now. So starting off with question 14, I just want to do an easy one first. I want to find the derivative of inverse tan x by using this standard integral formula here. So remember, this is what's given to us. And from there, I know that the derivative of this equals to that. And also from there, I know the derivative of inverse tangent equals to a on this. But in this case, it doesn't really matter because a just equals to 1, so that's just 1 anyway. So that means this just becomes 1 on 1 squared, which is just 1, plus x squared, okay? And that's just your general formula as well. All right, so same idea as inverse sine and cosine, yeah? Great, let's have a look at question 15 now. So we have this memory box up here. You can see that we have our general formula down the bottom, and up the top we have our altered formula. Remember how we went through those steps? Now we'll be using this formula up here when you see there's a denominator, well, whereas we're going to be using the general formula when there's not a when the denominator is just 1, yeah, because it's just the easiest way. So here you can see the denominator is 6, so we'll be using the formula up there. So I know that a equals to 6, so I just need to substitute 6 into this formula. So up here, a becomes 6, and that a squared, so 6 squared becomes 36 plus x squared there, okay? All right, so now let's move on to something a little bit more difficult. So question 16 here, I want to find the derivative of inverse tangent of 5x. And because it's 5x, I'm going to need to use the chain rule. So in the same way as when I emphasized it before, this here, I want you to substitute in the whole thing, okay? Otherwise it'll be completely wrong. Best way to do that is put brackets around it so you remind yourself to square that 5. And now multiplied by the chain rule of the derivative of 5x, okay? So that just becomes 1 on 1 plus 25x squared times 5. Just put it together and it becomes 5 on that. Now you can see in this question we use the general formula here because the denominator is 1, yeah? Can you see how it would be more difficult to use this because a essentially is just going to be 1 and it's unnecessary extra steps that you're going to do. And as we all know in our maths exams, the time is really, really important. Okay, so that was question 16. Now having a look here, we want to differentiate inverse tangent of 2x minus 1. Well, this is a whole equation, so obviously we're going to need the chain rule as well. So this whole thing is what x equals to, yeah? So I substitute that whole thing to b squared and multiplied by the derivative of that. Now, this just becomes 2, doesn't it? So we'll just be multiplying by 2. Now, over here, let's expand that. So we have 2x minus 1 squared. So square the first, so that becomes 4x squared. And negative 1 times 2x becomes negative 2x, times that by 2, yeah? So that becomes negative 4x, and then square the last one. So that just becomes plus 1. So now I have 4x squared minus 4x plus 1, and there's additional plus 1 there. Okay, so that just becomes plus 2. Yeah, and that's, I factorize out the 2. So 2x squared minus 2x plus 1. And this 2 here cancels with that 2 there. And that's how you get the final answer as 1 on 2x squared minus 2x plus 1. Yeah? So it's good to just work those things out. You can do it on the side or you can do it in the same process, whatever's up to you. And then remember to just always try and put it together in one fraction at the end because the answer just looks better in that way. All right, great. Let's move on to question 18 now. So here we want to differentiate inverse tangent plus 1 and to the power of 4. And so whenever you have to the index of something, you're going to be using the chain rule. So I'm going to take the 4 down and that becomes 3, yeah, subtract 1 from that. And now I'm find the derivative of what's inside the bracket there. So that just is going to stay. I'm not going to try expand it or anything like that. And this, the 1 just disappears, doesn't it? When you differentiate 1, it just becomes 0. So I only really need to differentiate this and I can just apply the general formula here and go straight to this and work out that's going to be 1 on 1 plus x squared. Yeah? Great. So, even though that did look quite difficult initially, it wasn't that hard a question, was it? All right, let's have a look here. We want to differentiate inverse tangent of ln x. Now, we haven't worked with ln x in this module yet, so do you guys remember what the derivative of that is? So, because that's not just x, we're going to be working with the chain rule. This just becomes ln x squared, and we want to find the derivative of that. So, do you guys remember what that is? Yeah, great. The derivative of that is just 1 on x, like that, okay? And so our final answer is just going to be x multiplied by that. You don't need to expand that or anything like that, yeah? That's completely fine for your final answer. I think as long as it's in one fraction here, that's completely fine. All right, so that was working with ln x. Now, what happens when you have ln of inverse tangent x on 2 and you want to differentiate that? How does that work? Well, here, the first thing you want to do is just work with the ln, yeah? And remember, when you differentiate ln, it just becomes 1 on that, and then it multiplied by the chain rule, essentially. So it becomes 1 on inverse tangent of x on 2. And now you have to multiply by the chain rule of what's inside the bracket, okay? And so let's work this out then. So over here, because you can see that the denominator is 2, which means I want to be using this equation up here and not the general one that we've been using previously. And because a equals to 2, I just substitute in 2. So that becomes 2 on 2 squared plus x squared. Yeah, can you see that? And like previously, just simplify a little bit. So the 2 squared just becomes 4, and I just can put that in a bracket, multiply it by that, and the 1 times 2 gives me 2 on top. Yeah? And you can write that as your final answer there. So just remember, when you see a denominator and it's not just 1, you want to be using a different formula than the general formula. Okay, let's have a look at something which is quite interesting. So question 21 here, I want to differentiate inverse tangent of sine of 2x. So can you see how this is a 3-tiered equation? So we have inverse tangent, and then we have sine, and then we have 2x here. So in this case, it means I need to apply the chain rule twice, don't I? So once for the inverse sine, and the second time for the 2x. Yeah? Okay. So what I like to do is just apply the first chain rule and then can apply the second chain rule, yeah? Some of you like to apply all the chain rules in one go, whatever you prefer is fine. So here, this whole thing is my x, isn't it? So that's why I've substituted that whole thing into the equation. So it becomes sine squared 2x plus 1, multiplied by the derivative of sine 2x. Now that just becomes cos 2x, and now I want to apply the second part of the chain rule, so derivative of 2x, and that just becomes 2. So I have 2 times cos 2x, and the bottom can just stay like that, yeah? So what's really important to be careful of here, that it's a 3-tiered equation. So don't forget your second chain rule with the 2x there, because it's easy to, because it doesn't come up that often and you think, oh, I've used a chain rule for sine, but if that's anything other than just x or x on a denominator, we have to use a second chain rule as well.